acid-base titration. Okay? Titration is a method. It's a method, it's a laboratory method of determining the amount of acid or base in a solution. And it uses solution stoichiometry, which we just learned about. So in a titration, which is what we're doing in lab today, we have a substance in a solution where we know the concentration, and we're going to react that with another substance in a solution where we don't know the concentration. The idea is to find the concentration of the solution that we don't know. So we know one solution concentration, we don't know the other one. Typically, or the most common type of titration is an acid-base titration. When we have most acids and bases, we end up with the same net ionic equation. So if we have hydrochloric acid and sodium hydroxide, the net ionic equation is hydrogen ion plus hydroxide ion gives water. The chloride ion, the sodium ion are spectators. They don't actually participate. So in an HCl solution, because the chloride ion is a spectator, we're going to ignore it for clarity in our diagrams. So here's our representation of the HCl solution. So these are the hydrogen ions. There are chloride ions in there, but because they're not going to do anything, we're going to ignore them. You cannot have a solution just of hydrogen ions. It's not possible. So what we're going to do, and this is actually what we're going to do in lab today, is we're going to take a solution of sodium hydroxide, where here again, we're not showing the sodium ions because they're spectators and they don't do anything. They just hang around. We're just showing the hydroxide ions. We're going to take a solution of sodium hydroxide where we know what the concentration is. And we are going to add this to a solution of acid whose concentration we do not know. As we add the hydroxide to this acid, it will react and form water molecules. So these hydroxide ions are coming in and they're taking out the hydrogen ions. At some point, we will add an equal number of hydroxide ions to the number of hydrogen ions that we had in the solution. This is called the equivalence point, where we have equal numbers of hydroxide ions and hydrogen ions, and they form water, and at that point we have no extra hydroxide ions, we have no extra hydrogen ions. Everybody got matched up perfectly and nobody's left out. That's the equivalence point. Well, how do we know when we've done that? We use an indicator. If you notice, this solution is pink, and that's not just to highlight it. We're actually going to see pink color today. The equivalence point is usually signaled by what we call an indicator. The indicator indicates when we're done, right? Indicators are generally dyes. They're complicated organic molecules that are sensitive to hydrogen ion concentration. And so their color will change if they're in an acid or in a base. So usually how this works is we have the concentration of one of the reactants being unknown and the other is precisely known. And so by measuring the quantities of each, we can use solution stoichiometry and calculate the unknown concentration. Here's actual photographs of a titration. Here we have, this is a burette with sodium hydroxide in it. Looks like water because sodium hydroxide solution is colorless. Here we have a flask containing hydrochloric acid and an indicator called phenolphthalein. There's a lot of phenolphthalein, so we'll work on pronouncing that today. This has phenolphthalein in it. Phenolphthalein is colorless in an acidic solution. This is acidic, so it's colorless. When it's in a basic solution, it turns pink. So as we add the sodium hydroxide, we'll see a little bit of pink form because it hasn't completely mixed up yet. So right here where that drop fell in, there's a localized high concentration of hydroxide ions. But then we're going to swirl the flask and mix it so that the hydroxide ions can react with the hydrogen ions. The pink color goes away very quickly. And we'll keep doing that. We'll reach the equivalence point, and the next drop will cause the solution to turn pink and stay pink. Okay? So when we get to a stoichiometric proportion, 1 mole of OH minus for every 1 mole of hydroxide ion, the indicator changes to pink when we get just a teeny tiny bit past that. And we're so close to it that the amount we went over doesn't matter at all. So what you'll find in lab today is that you're aiming for this really pale pink color, and you're going to end up with fuchsia a lot, kind of about the color of my iPad case here. And that's okay, it'll happen. But we're going to try for pale pink, blush pink, pink that lasts like 30 seconds and then kind of slowly disappears. So let's do an example of a calculation. So the titration of a 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of 0.158 molar KOH solution to reach the equivalence point. What is the concentration of the unknown H2SO4 solution? Aren't you glad we didn't look at questions like this at the beginning of the semester? Hopefully it doesn't seem so overwhelming. You're like, well, I think I have a clue what we should do here.
22.87 milliliters for every mole for 1.58 moles.
We're using 22.87 milliliters of this solution. This is moles per liter. We're gonna have to do some units and stuff, but the first thing we need an equation, because this ends up being stoichiometry, and so we have to look at the equation, and then having the written out equation is going to give us somewhere to put these numbers. So we need to write the equation. So we've got H2SO4. Yeah, enter drawing mode first. H2SO4 reacting with KOH, leaving a space there in case I need to put a coefficient. We can treat these like double replacement. So this is H plus and SO4 2 minus. This is K plus and OH minus. Just taking the acid and the base and separating into the ions that they form. Sulfate ion with hydrogen ions. And then we're going to swap partners. So we're going to end up with H plus pairing up with the OH minus, and that forms water. And we'll have K plus pairing up with the SO4 2 minus, and that's going to form K2 SO4. Any questions? We talked about triprotic, diprotic, monoprotic acids real briefly. What kind of acid is this? It's a diprotic. So a diprotic acid, we're probably going to need 2 KOH. And if we look at this, how many Ks do we have over here? We've got 2 of them. Oops. So we put a 2 in here. So we've got SO4 and SO4. 2 Ks, 2 Ks, and then here we've got 2 hydrogens and an oxygen and 2 hydrogens. So over here, what do we need? We need a 2. So we've got a total of 4 hydrogens and 2 oxygens, and there's our balanced equation. I'm going to get rid of this, our little showing our work down here because we need it for more work. So you have to start with the balanced chemical equation. Now we can take the numbers from our problem and put them in here. 20 milliliters relates to which of these compounds? The H2SO4. I'm going to put 20.0 milliliters. And 22.87 milliliters pertains to which one? The KOH. So 22.87 milliliters. And the concentration, 0.158 moles per liter, of the KOH. But I'm going to write that moles per liter. What are we trying to find? Concentration of the H2SO4. So we're looking for, question mark, moles per liter. So this is a tiny bit different than the solution stoichiometry that we did, because there we were looking for a volume. Now we're looking for a concentration. We're given the volume. What information do we need to find the molarity of that H2SO4 solution? Molarity equals what? Moles of solute per liter of solution. They're giving us the volume. What we need to find is the moles. If we find the moles and then divide by the volume, we'll get the molarity, right? So let's squeeze our path in over here. We're starting with milliliters. Well, let me ask you this first, because there's a couple different ways we can do this. You guys comfortable with converting milliliters to liters? What do we do to do that? Multiply by 10 to the minus 3, or just move the decimal point 3 places to the left, right? So let's just convert these. Let's see, what's the best way to do that? I'm just going to convert these to liters. So 22.87 would be 0.0, right? 2287. Because I took that decimal point and I went 1, 2, 3. And 20 milliliters would be what? 0.020. Cross that decimal point off. And then get rid of the milli. Is everybody okay with that? You're certainly welcome to write it all out. I don't have a lot of space on this slide. So converting those to liters up front can make things a little simpler. So now let's look at our path. We're starting with liters of KOH. And from that we can find what? Moles of KOH. And from that we can find moles of H2SO4. Stoichiometry was grams to moles to moles to grams, right? And then we learned that it could also be liters to moles to moles to liters. Well, here we want to stop at moles. So we're going to go liters to moles, and stop. And then we're going to put it into this equation and find the concentration. So we've got our liters of potassium hydroxide, 0.02287 liters of KOH. We're going to have two conversion factors. Liters to moles to moles. That was our path, liters to moles to moles. So here in our equation, we've got liters to moles to moles. Then we're going to put our units in so they cancel out. Liters of KOH are canceling, and moles of KOH down here to cancel the ones on the top over there. Moles per liter is the concentration. This is the concentration that we know. We know the concentration of KOH. So 0.158, 0.158 moles. How do we find this relationship?
That equation.
From the equation. 1 mole of sulfuric acid reacts with 2 moles of KOH. So I put 1 in front of H2SO4 and 2 in front of KOH. And now I can find the number of moles of sulfuric acid that were in that flask. 0.02287 bless you, times 0.158 divided by 2. 0.0018 180673. I'm just going to leave them all there. It's just going to stay in my calculator anyway. H2SO4. How many significant figures would that number have if that's the end of our... We'll have 3. This volume had 4. This concentration had 3. So this 0 is the last sig fig. I'm just going to carry the extras around to avoid rounding errors. That, wrong button. That is the number we need up here. 0, well, I'm going to have a problem. Because I'm going to write in black, and it's not going to show up over there. 0.00180673 moles. And what was the volume that we divide by? 20 milliliters, which is 0.0200 liters. I still have that number of moles in my calculator, so I'm just going to divide by 0.02. And I come up with a concentration of 0.09. Now I'm going to round to 3 sig figs. 0.3 molar. That is the concentration of the sulfuric acid. There are other ways to put it together. So if you want to do it a slightly different way and you're coming up reliably with the same answer, that's fine. Different ways make sense to different people. Any questions?